All right. So let's just keep going with the next two topics we're going to do today. We're going to do 5.5 and 5.6. We've actually talked a lot about both of these topics before, so this should be short and sweet. Um, we'll introduce a couple new things to them, but it shouldn't be too bad. Okay, 5.5 is called the collision model. And if you go back to 5.1, we talked about this a lot and about the factors that affected this. Okay, we said in order for a reaction to happen, molecules actually have to collide with each other. Okay, simple as that. Okay. Well, it's not quite as simple as that because we learned that there's a couple things that have to be in place for the reaction still to happen. You can't just have two things collide and they react with each other. We also saw we tied that to the reaction rate. If I have more collisions happening, the reaction rate is going to increase. That makes sense. And as concentration increases, that's going to increase the number of collisions, so it will have an increase in reaction rate, right? All very logical stuff here. Now, this collision model says a few things. This is all the different things that have to happen besides just a collision, okay? Right? The first thing is definitely the particles actually have to collide for a reaction to happen. And that the rate is dependent on the frequency, how many of these collisions happen. The second thing, and we've mentioned this before, is that they have to have enough energy when they collide. Because the molecules already are bonded to each other. And so in order to react with stuff, I usually have to break those things apart. And so I have to overcome the energy inside, a lot of times, those covalently bonded molecules. That's what's called the activation energy. The energy that's going to be needed to break the bonds of our molecules. And then the last thing is the particles have to be in the correct orientation. A certain part of a molecule has to hit a certain part of another molecule in order for the reaction to occur. So all three things actually have to happen simultaneously for the reaction to happen. They have to collide with enough energy, and the right parts of each molecule have to collide with each other. Topic 5.6 is us getting into this graph and all the different pieces of it, so we're going to see this graph a whole lot. Okay, so we'll analyze this in a second. But all you need to kind of look at this is we have reactants on one side, products on the other side. It's kind of like a time axis down here and energy axis on the y. So originally our chemicals are just sitting there, right? I have chemical in one beaker, chemical in another beaker. They have energy stored inside of them because they're bonded. And if I can break those bonds, I can release that energy. So there's energy inside of them. In order to get them to react, I have to collide them with enough energy. That energy is called the activation energy. That's kind of the size of this hill right here. Okay? So this says if sufficient kinetic energy, kinetic, right, is the energy of motion, that's the energy of the collision. If we have enough of that kinetic energy to overcome this potential energy from right here, the molecules are going to form what's called a transition state. That's kind of like, if you think about, everything's actually going to be broken apart. Every piece is kind of broken apart for a moment in time. That's the top of this hill. We call that the transition state. It is also called the activated complex. We'll use those terms interchangeably in this class. So it says, if that kinetic energy is big enough to break the potential energy, it forms that transition state in which the reactant bonds are breaking and the product bonds are going to form. We've essentially gotten to the top of the hill, and so what happens then? You just slide down to the bottom and form products. Okay? Easy. Now, this whole orientation thing, this is the tricky part. Okay? We have a reaction up here at the top. I have nitrogen dioxide and carbon monoxide reacting to do nitrogen monoxide and carbon dioxide. All right? Now, in order for that reaction to happen, if I look at what's going here, one of these oxygens is leaving the NO2. Well, that oxygen is not going to be bonding to the oxygen part of CO. Right? It's going to be bonding to the carbon part of CO. So if those oxygens collide with each other, nothing's going to happen. If the nitrogen collides with that oxygen, nothing's going to happen. If the nitrogen and the carbon collide with each other, this reaction won't happen. What I need to happen is right here. I need one of these oxygens to collide with that carbon with enough energy to cause this NO bond to break. Right? There's some electrons transfer, right? There a whole bunch of stuff ends up happening here. Right? It's not as simple as this, but whatever. And then it forms this, what we want. So in most reactions, molecules must be oriented in a certain way for a reaction to occur. All right? Sometimes it's easiest if you draw these things out to see what actually has to react, what actually has to collide in order for that reaction to happen. We also know that collisions are occurring all the time, but not all collisions result in a reaction. I have two bolded terms here that we need to know. Most of our reactions, if we actually go back here, like look at this one, how many molecules do I need for this reaction to happen? 2. And if we go back and if you look at most of our reactions, most of them only need 2 molecules to react. We very rarely have reactions with 3 or 4 or 5 molecules. If a reaction only has 2 molecules needed to react, we call that a bimolecular reaction. And if we think about that, because what I'm saying is I have to have only 2 molecules that are colliding at the same time with the same energy, or with enough energy with the correct orientation. The chances of that are pretty high if I only have 2 types of molecules floating around. But if I need a trimolecular or higher reaction, where it's not going to happen maybe in multiple steps, I actually literally need 3 different molecules to all collide at the same time, and they all have to be oriented the same way, or the correct way, and they all have to collide with enough energy, that's unlikely to happen. Trimolecular reactions are very seldom seen. Most things happen in bimolecular steps. Now, sometimes our overall reaction does show multiple, like trimolecular, a whole bunch of different molecules. But as we saw in 5.4, most of those reactions do not happen in one step. They happen in multiple steps. And each one of those multiple steps is usually a bimolecular or a unimolecular thing decomposing. Very rarely do you have a single step happening that is trimolecular or higher. Which, if we go back to 5.4, one of the things that you have to be able to do is come up with a plausible mechanism for a reaction. One of the things that they like to ask you about is you might be given 2 very plausible mechanisms that add up correctly, right? They do all the things that we need to do, but one of them has 1 step in there that's trimolecular, and the other one doesn't. Well, the trimolecular one is probably not the correct answer then, because a trimolecular collision is unlikely to occur. So keep an eye on that. All right, these ones, we saw these in 5.1, all these different factors that affect the reaction rate. Okay, increase the surface area, increase concentration, increase pressure, increase temperature, add a catalyst. All of those are going to increase reaction rate. We talked about those in 5.1, and all of it makes sense. There's nothing out of the ordinary here. All right? And that's it. That's 5.5. Super easy. So we can see here, this says, given the following reaction, which set of reaction conditions will result in the highest reaction rate? Okay, well, I need these things, right? I want the combination of that's going to give me the highest version of all of these. So, right? The key thing here is the volume of the container changes. So, like step 2 here, I have twice as many moles, but I also have twice as much container in here. So my concentration actually didn't change between experiment 1 and 2. My concentration actually in experiment 3 is twice as much as experiment 1 or 2. because the volume is half. Okay. So on this one, yeah, I believe experiment 3 would give us the highest reaction rate because it's the highest concentration. They're all at the same temperature. They're all at the same pressure, we would assume, or something like that. Okay. So concentration would be highest. So watch that volume. And then this last one, let's look at this. We love Maxwell-Boltzmann distributions. We have two different graphs here, so it's just kind of asking you to draw some stuff. On the first graph, add a vertical line to represent a low activation energy. So let's see here. Can I draw on here? I think I can. Let's do a pen. How exciting. Okay. A low activation energy. Perfectly straight line. Okay, beautiful. On the second graph, add a vertical line to represent a high activation energy. I'm actually going to do it on the same graph. I'm just going to do it in a different color. Okay. Do it in a nice pink. A very high activation energy, something like way up here. Okay. All right. Now, if I think about what that means, if the activation energy was this pink, perfectly straight line, really, I need this high temperature curve to occur. Because if I was at 100 degrees Kelvin, none of my molecules have enough energy to react. I need the added kinetic energy that comes with the increased temperature. Because remember, go back to unit 4 or 3 or whenever we were talking about this. Temperature of gases is directly proportional to kinetic energy, which is proportional to temperature. All right, but if the activation energy is low, we can actually see increasing the temperature. It says, why don't we see a large increase to the reaction rate? Because we actually drop the number of particles that are at that temperature, that are at that energy. If we think about what this means or under that energy, okay, what we're looking for here is, okay, I'm going to go back to red here. The amount of energy I need is this amount or higher. Well, that would be everything to the right of that curve. Okay. So which is like, I don't know, 2/3 of the red curve. The blue curve, it's maybe, I don't know, 80% of the blue curve. It's maybe 90% of the green curve. So the actual change isn't that much higher versus this pink curve where you're going from 0% to 20% or something like that, okay? So that's a bigger increase. Simple enough? All right, cool. All right, that's 5.5. So let's do 5.6. Oh, let's move me. Slideshow. 5.6. Reaction profile diagrams. I said we were going to see these diagrams again. Well, here's that same graph that we saw in the previous one. These reaction profiles, and you saw these in first year chemistry, right? There's a reason I spent some time on that stuff. Y-axis is usually potential energy. If you're given a unit, potential energy in chemistry is often measured in kilojoules per mole. The joule is a unit of energy. So kilojoules per mole. The x-axis is actually called something called the reaction coordinate, which is the progress of the reaction. A lot of times you'll see it's labeled as reaction progress there. Just think of it as a time axis, okay? This is before the reaction happens. Your reactants, okay? You're going to have a flat line at the start because you just have different beakers that have each reactant in there. And they're just sitting there with their energy stored in their bonds. All right? We then mix them together. That's what this hill is. They're being mixed together. They're colliding, right? They're breaking apart. That's the transition state, that activated complex. And then they form the products. Once they form the products, it's another flat line because the products are now stored in their beaker or whatever, and they have new bonds that are at a new type of energy. So this end here, a lot of times I call it the tail, can either be below the reactant energy or it can even be above it. But it's going to be a flat line. Now, this activation energy shows up on this graph. Activation energy, we call this EA, a lot of times is how it's labeled. Okay, right, and that we know that's the energy of the collision to break it apart. On this graph, EA is the difference in energy, okay? Difference in energy between the reactants and the top of that hill. It's essentially how high of a hill is that. The height of that hill is the amount of energy we have to add to break these things apart. That's the activation energy. When they get up there, the top of that hill, again, is called the transition state or the activated complex. Everything's broken apart. Everything then falls down the hill to your new energy on the other side. All right. And that's what this is, right? The transition state is this intermediate point between two stable compounds. They were stable as the reactants. They were stable as the products. They are unstable in the transition state. But they are colliding, and they're going to proceed over that hump there to form the products. Now, this says if the energy of the transition state is greater, if EA is bigger, that hill increases its size. If that hill is a bigger hill, fewer molecules are going to have enough energy to climb that hill. If fewer molecules have enough energy to climb that hill, the reaction rate is going to be slow. So large EAs correspond usually to low reaction rates. Low EAs usually happen faster. Again, it should make sense. And we can calculate this, right? This graph has no numbers over here, but we could add numbers there. And so you could actually calculate it. If this had labels, right? If this reactant was at 15 kilojoules per mole, and the top of this hill was at 35 kilojoules per mole, EA would be 35 minus 15, so the activation energy would be 20. That's a pretty easy calculation. Now, if you also go back, remember we started to talk a little bit about that reactions can go forwards or backwards. We were talking about that when we were introducing the strong and the weak acids. And so if some of the reaction is going backwards, the backwards reaction has a different EA. Because on this one, it's actually going to be bigger because it has to climb a bigger hill going backwards. And we could calculate that again if we had numbers on here. Okay? So that's not too bad. But we could also see that if we relate it to reaction rates like we talked about the previous one, the forward reaction would probably happen faster than the backwards reaction because EA going backwards is bigger. Now, we can talk about this energy, and we're going to talk about it, and we're going to love this in Unit 6. But we've mentioned this term enthalpy before. And usually enthalpy, just think of it as energy. Our enthalpy, we usually talk about it in terms of a delta, a difference in energy, okay, a difference in enthalpy. So if I have this graph here, the enthalpy of the reaction, the energy of the reaction, is going to be the energy difference between the products and the reactants. Well, if my graph here, it shows me, here's the energy of the reactants, here's the energy of the products. Subtract those two numbers. Now, remember, there's a correct order to subtract these things. Anytime you see the delta, the triangle, final minus initial. Products minus reactants. Do not mess that up. Because if you do, the magnitude of the number you get will be the same, but the sign will be different. And the sign is usually what we care about. All right? Because the sign tells us if it's an exothermic reaction, which releases energy, think of something blowing up, and an endothermic reaction, which absorbs energy. Endo is like inside, exo is outside. So an endothermic, it's absorbing energy from something. All right, this is ice melting. It's absorbing heat from the surroundings to melt. All right, so if I subtract products minus reactants and that tail is lower than the reactants, that delta H is going to be a negative sign. Delta H is negative, it's an exothermic reaction. That's a release of energy when that reaction happens. Endothermic reactions, the product tail is above the reactants. That delta H would be a positive number. It's an endothermic reaction. those products have absorbed that much energy, and so their actual energy inside those bonds is higher than the original energy. All right? Get very familiar with these graphs. Be able to calculate the activation energy. Be able to calculate the delta H. Do not calculate your delta H as a difference from activation energy to products. It's reactance to products. All right? Okay. Now, the other thing is we started saying that reactions usually happen in multiple steps. Elementary steps, right? And we can have a mechanism of those steps, be able to propose it, be able to validate it, all that. The slowest step, if we go back to what we just talked about with activation energy, higher activation energy usually means slower reaction. So the slowest step will likely have the highest EA. Now, multiple steps means there's going to be multiple humps, multiple hills. If we had a 4-step reaction, there's going to be four little humps on that diagram. So that's one really easy way to tell if you have a mechanism there and how many steps it is count the humps. Okay. Each hill will have a different transition state, different activated complex. All right. The tallest hill is the slow step, your rate determining step. So in this one, it would be step 1. Because the other thing to think about here, when I'm climbing hill 1, I'm starting from the reactance and I'm climbing this whole stupid hill. I then fall down that hill because I'm making like an intermediate or something, right? And then now I'm using that intermediate to do something else. And so I've fallen down the hill somewhat, and now I'm climbing another hill because it's doing another step. The EA for the second hill is the difference between the bottom after this first step and the top of that second hill. It is not the difference from the reactance to the top of that second hill. It is from the base where it falls to the top of that second hill. All right, which is a much smaller hill, so it goes very fast, right? And we said we don't care about the fast steps in terms of the overall rate. It just goes too fast. Be able to identify which step would be the slow step from a reaction mechanism diagram or reaction profile. Be able to tell me how many steps a reaction would take from a diagram like this. 2 hills, 2 steps. Big hill, slow step. I could come up with a rate law then if I knew what was actually happening there. Well, speaking of rate laws, we can actually do some stuff with them. Okay, we have a basic little Maxwell-Boltzmann diagram up there. Here's the activation energy labeled on there. We know that the basic rate law, right, is rate equals K times concentration of A to the M times concentration of B to the N. And I also mentioned that K is dependent on temperature, which is why the problems always tell you what temperature it's at. And you guys are always like, what do I do with that number? You do nothing with that number. It's just information. Because that value of K depends on that information. All right? Now, I know that if I change temperature, it's going to change the energy of the molecules, as we see from the Maxwell-Boltzmann diagram, right? So T3 is bigger than T1. It's changing the energy. Now, what it does not change is the actual reaction mechanism. The actual energy of those transition states does not change. This is just giving us more molecules to get over that activation energy. So nothing really changes with all this stuff. It's just changing how many molecules can accomplish that, right? But it does change our rate law if I change temperature, because it's going to change K. All right? It's going to change K. It says the different value of K can be accounted for by a larger proportion of molecules that have enough energy. Right? Now, so that's one thing here. Okay, is K is temperature dependent. You're going to hear this a lot in Unit 7. Okay? That K is temperature dependent. It'll be a different K, but it will still be temperature dependent. All right? Catalysts. We're going to see more of this in 5.11. That's the last topic in this, so we'll talk more about catalyst. But here's the thing. Catalyst, we said that's one way we can increase the reaction rate, make it go faster. So really what a catalyst does is it lowers the activation energy. And it does that usually by adding additional steps into the mechanism. Okay? So, like, here's one. That would be a single step reaction in that purple, very large EA. We add a catalyst, it then creates a 3-step reaction. All right? But all of those steps have lower EAs. And really, we would actually have numbers here to figure out what the slow step is, but because it looks like EA1 and EA2 are pretty much the same here, okay? But the start step and the end step are identical. Same products. All right? The catalyst is, it's pooped out at the end, so it doesn't show up in the reaction. Easy enough. Sketch a diagram for an endothermic reaction. Okay, here we go. There's my axis, endothermic. Flat, there's my hump, and it ends up higher. Okay, again, perfectly flat line right there. Beautiful. Okay, all right, that's it. Okay, hopefully, I'll be able to see you guys sometime soon. Okay, till then, keep on keeping on.